All right, picture this. You stumble upon a vial of some mysterious liquid. What is it? Could be anything, right? A new medicine, maybe a rare perfume, or hey, maybe something dangerous. So how in the world would you know? Well, today, we're going to dive into the super cool forensic science that lets chemists solve these exact kinds of molecular mysteries, figuring out the identity of pretty much any substance, right down to the atom. So yeah, let's really put ourselves in the shoes of a scientist for a minute. You're in the lab, you see this vial. It's just a clear liquid, no label, no clue what it is. Where do you even begin? And this isn't just some made-up scenario, you know? This is a real-world puzzle that chemists solve every single day. You can really think of this whole process as a chemical whodunit. It's a mystery. And just like any good detective, scientists aren't just guessing. Nope, they've got this specialized forensic toolkit, and it's designed to make the invisible visible and crack the case wide open. And the challenge here, wow, it's just massive. I mean, we're trying to build a perfect 3D blueprint of something so tiny that even the most powerful microscopes can't see it. They're just useless. This is detective work on a scale that is, frankly, mind-boggling. So, what's the secret? Well, the key is a set of techniques called spectroscopy. The best way to think about it is as the forensic toolkit for these molecular detectives. It doesn't use sight. Instead, it uses different kinds of energy, like light, to basically interrogate the molecules, to force them to give up their secrets. Okay, so where does our investigation begin? Well, you start with the most basic fact you can possibly get, the molecule's weight. This is our very first clue. The first tool we're going to pull out of our toolkit is called mass spectrometry. And really, the simplest way to think about it is as a hyper-accurate scale. Seriously. But instead of weighing, a bag of apples, it weighs a single, individual molecule. It's that precise. So we take our mystery liquid, we put it into the mass spectrometer, and boom, it spits out a number, 102. What does that mean? It means one single molecule of our substance has a mass of 102 atomic mass units. Okay, now we're getting somewhere. This is our first solid piece of evidence. So what good is that number? Well, it's huge. See, scientists know the exact weight of every atom. Carbon is 12, hydrogen is 1, oxygen is 16. So you just do a bit of chemical math and you can figure out which combination of atoms adds up to 102. For our mystery molecule, the most likely combo is C5H10O2. That's 5 carbons, 10 hydrogens, and 2 oxygens. And just like that, we've gone from an infinite list of suspects down to just a handful. That's a huge first step. Okay, that's a great start, but there's a problem. A formula of C5H10O2 could still be put together in a bunch of different ways. We need to look deeper, inside the molecule. So let's move on to our second clue, the vibrating bonds. Now, the idea behind our next tool is it's so cool. It turns out that every single chemical bond inside a molecule is constantly vibrating. And here's the kicker. Just like a guitar string, each type of bond, whether it's between a carbon and an oxygen or a carbon and a hydrogen, vibrates at its own unique specific frequency. And to stick with that guitar analogy for a second, think about it this way. Really strong, tight bonds, like a carbon-oxygen double bond, they're like the thin, taut strings on a guitar. They vibrate at a really high frequency. But the weaker, looser bonds, like a single bond between two carbons, they're more like the thick, loose strings. They vibrate at a much lower frequency. And guess what? We can actually measure these unique vibrations. We use a technique called infrared spectroscopy, or just IR for short. So we zap our sample with infrared light, and we see this huge signal pop up at a specific high frequency. That is the telltale signature of a C double bond O, which is part of a specific little arrangement that chemists call an ester. It's like finding a specific Lego piece. We now have a parts list. We know for sure our molecule contains this exact piece. All right, so we've got the formula, and we've identified a key component. Now we need the final clue, the one that puts it all together. It's time to get the atomic blueprint. So our final tool, and honestly the most powerful one in the box, is called nuclear magnetic resonance, or just NMR. If mass spec was our scale and IR gave us the parts list, then NMR is like a molecular GPS. It literally maps the exact position of every single atom in relation to all the others. NMR gives us 3 absolutely critical pieces of information. First, it tells us how many different kinds of hydrogen atoms we have. See, a hydrogen stuck to an oxygen feels different to the machine than one stuck to a carbon, so they give off different signals. Second, it actually counts how many hydrogens are in each of those unique spots. And third, and this is the real clincher, the signal for each group of atoms gets split by its neighbors. This splitting pattern lets us map out exactly which group is next to which. It reveals the complete atomic blueprint. It's amazing. Okay, with that GPS data in hand, we have everything we need. All the clues are on the table. It is time to close this case. So let's put it all together. Let's assemble the evidence. Clue number 1 from the mass spec gave us our formula, C5H10O2. Clue number 2 from the IR spec told us it has a very specific part, an ester functional group. And finally, clue number 3 from the NMR gave us that final blueprint, showing us exactly how all 17 of those atoms are connected to each other. And the mystery is solved. When you put all those clues together, there is only one possible structure it could be. Our unknown substance is ethyl propionate, which is a compound that's sometimes used because it has this nice fruity smell. You know, solving a little puzzle like this is pretty satisfying. But why does this kind of molecular detective work really matter? Well, its impact is absolutely enormous. It plays a fundamental role in fields from medicine to the environment to the technology that literally shapes our world. I mean, these very same techniques are used every single day to design new life-saving drugs, to identify and track dangerous pollutants in our environment, and to create the advanced materials that power all our technology. In fact, one of these techniques has a direct application that I can almost guarantee you've heard of. You see, the core principles behind NMR spectroscopy, that molecular GPS we were just talking about, are the exact same principles used in medical MRI scans. So instead of mapping atoms in a chemical sample, doctors use it to map the water molecules inside your body. And by doing that, they can get these incredibly detailed images of your tissues and organs. It has completely revolutionized modern medicine. So the next time you see a chemical formula, remember that there's this incredible detective story behind it. It really makes you wonder, right? If we can create a complete atom-by-atom blueprint of a molecule we can't even see, what other unseen worlds are out there just waiting for us to map them?